Hi, my name is Ken Lasterson. I wrote microbiomeprescription.com, and it's a system that uses expert systems. So I've been asked to explain a little bit more about expert systems, particularly for people who are microbiologists who may not be familiar with the process. So this is a presentation trying to explain to you what's going on and some of the characteristics. You may be interested in implementing your own expert system, which is awesome. Microbiome prescription is one approach, and as you will see, there are other approaches, and that depends on a bunch of factors, which we will discuss at the end. So, it's very simple. What is an expert system? Then we talk about a naive microbiome fact. Expert systems work as facts. Then we look at complex microbiome facts, and then we look at facts with probability. Although we're talking using the word facts, the word facts actually, with anything in the real world, which is not pure mathematics, is actually just probabilities. So we end up needing to modify the expert system to handle probabilities, not making an assumption that everything is a given fact. And then we'll look at the final tips and takeaway about expert systems, some issues that if you are wanting to create your own expert system or you need to create your own expert system, you need to consider. So first question is simple. What is an expert system? Well, I could give a variety. It's basically a software program which emulates what an expert, keyword expert in the field who is well read, would do to reason out a solution to a problem. So what it basically is trying to emulate the expert thinking. Current things like large language models and ChatGPT can do it to some degree. However, the expert system is a little bit finer and more precise because the information that goes into it is curated, and there's a very strict discipline that should be happening with large language models, etc. The matching and everything else tends to be a little bit shoddy at times, resulting in things called hallucinations. Now, the oldest expert systems dates back from the 60s and 70s, and they actually were found to be highly effective and did something like 95% better than a non-expert in dealing with issues. In other words, you had your specialists in a particular area, and what they would conclude, and if you take a look at the typical MD, and what they would conclude, the expert system, when the same data was given to it, would match the well-versed experts far more accurately and better than the typical MD. In other words, superior and probably a good adjunct, not a replacement, but an adjunct to practical medical issues. So let's take a look at a way of visualizing a expert system, and that is as a decision tree. So we end up with the first, for example, this is the diagnosis tree. You take the first one, is the first lab result true or false? If it is, then we go on to the next one, and based on that one, we ask the next question and the next question and next question until we get to a possible thing. Some cases we have something like an uncertain configuration. In other words, the existing decision tree is not sufficient to resolve the question. Other time we end up with a very clear answer, or suspicious, etc. So there's a variety of outcomes possible. When we're dealing with microbiome and trying to correct it, we don't want to end up with uncertain suggestions if we can avoid it. If the initial take-through comes to uncertain suggestions, what we want to do is loosen the terms so that we are going with the most probable, keyword probability, most probable suggestions to help, so that the patient at least have something to work from. Just simply say, oh, we don't know what going. For the microbiome is generally actually not necessarily truthful, but also not what the customer, the user is expecting, the client is expecting. And my general impression is we can always make suggestions. They may not be the best, but we always can get some reasonable suggestions that should result in some improvements. So how do you build one? Well, expert systems are programs which are a bit of a high technical problem in some domain. For example, medicine. It is an older field of artificial intelligence being used since the 60s and 70s. So we're talking about half a century have it been in. It is very different from popular AI, which are in the news like large language model, ChatGPT, etc. They are a different type of AI. It's sort of like saying, oh, this is a transport vehicle. Okay, yes, one happens to be cart and buggy, and one happens to be a Concorde jet. Both of them are transport problem. The newest ones is what's often popular. The oldest one, like a cart and belly or a plain old-fashioned Jeep to go through the mountain, may work better than trying to fly Concorde to your mountain cabin. So again, things change, and sometimes old technology has distinctive advantages over newer, more popular, more hot technologies. And what it does is it tries to capture in code the logic that a knowledgeable expert will use. It often performs better than a non-expert. For example, a primary practice MD using it will probably get better results than an infectious disease specialist who may use it but may frequently say, oh, wait a minute, I know it's this particular case and we should go this way, and the expert system doesn't capture it. And why it doesn't capture it? Probably because it doesn't have the data in it. Traditionally, how do we build an expert system? It's simple. You grab your expert or experts and you sit there and you grill them hour after hour, week after week to get them to explain all of their logic and all the factors they are doing it. And in some cases, asking them, okay, so you're saying this is there. Okay, what studies does that information come from? How do you know it? And you grill the experts for days and weeks there. And you are not going to have expertism better than the experts you're grilling. Now, here we hit an interesting gotcha. For the microbiome, most of the knowledge originates from studies. Our goal is to actually go to the source study to obtain better coverage of knowledge, more knowledge. In other words, as you will see later on, we may make use of 20,000 different studies to build our expert system. 20,000. Chances are your expert will never have in their life read 20,000 studies, perhaps 2,000 to 5,000 studies, and they may have learned additional things by hearsay. So in this case, we have, by going to the source study and being careful in the application, the ability to exceed that which the traditional grilling of expert system would be doing. So that's one of the key assumptions or beliefs about building it directly from studies rather than from the expert. We use the expert's logic and reasoning as a way of checking, and when we check the logic, and we go and we do some cross-validation using experts if at all possible, and see if they agree with the results or not. And if they agree with the results, good. If they don't agree, then we find out why they don't agree, and then we do a deep dive into the reasons for disagreement in order to improve the expert system. Regardless, there is human work involved. There is having to get experts involved. It simply cannot be done without both of them. Okay, let's start and let's look at naive microbiome fact. Basically, it's where logic can be captured in a very simple statement. If lactobacillus is low, then do a low glycemic diet. Okay, nice, simple, plain, ordinary thing. Sort of like a factoid, but basically it's a condition that results in an action. But we may also have some of these actions needing more conditionals in it. For example, low glycemic diet. Well, low glycemic diet doesn't work for everybody. If cholesterol levels are elevated, you don't want to do a low glycemic diet because that will make that condition worse. So we need to toss in additional terms there or condition. If a person is taking insulin, then basically the insulin dosage needs to be adjusted before going on the low glycemic diet and probably ongoing monitoring. So we're now getting into more complicated logic and more complicated rules. And this information has to be captured in the expert system as rules. And last one is low blood pressure. You don't want to do a low glycemic diet because that tends to drop blood pressure. Again, we end up having that the naive rule doesn't always work. There are a bunch of additional conditions which need or should be included with the information in terms of there. Whether or not it's included or whether or not you ignore them is a philosophical and a practical question. Basically, what we find is that the logic moves towards given this set of conditions, and the set of conditions are usually this condition and this condition and this condition and this condition, then implies a set of actions, maybe one action or maybe multiple actions. For example, lactobacillus low, then do low glycemic diet, eat plenty of yogurt, take lactobacillus probiotics, stop taking particular herbs which are known to kill lactobacillus, etc. So you can end up with your first statement and you can end up with a massive set of actions to be considered. Now, most of those actions have side effects on other things, so we have to end up having additional rules to prevent the side effects. So we end up with a bit of an interesting thing, but the catch is all this information should be coded into computer program, and then the computer program can logically, keyword logically, work through the consequences and get the results. One of the key things to do, which often happens from naivety, is that logic must be rigorously applied. For example, you could take the first statement and just flip it around and say, oh, wait a minute. If you don't do a low glycemic diet, then you're going to have lactobacillus to be low. No. Lactobacillus may be extremely high, and you're not doing a low glycemic diet. You may do something else that causes lactobacillus to be high. So it's a false reasoning. Similarly, doing a low glycemic diet will increase lactobacillus. That may also be false because the precondition before was low lactobacillus. If you already have a good level of lactobacillus, it may have zero effect, or in some cases, if you have high level of lactobacillus, it may actually drop the level of lactobacillus. So you cannot go and naively flip the logic around. So rigorous logic is needed. Typical findings often have many conditions that should be included as part of the conditions. For example, any diagnosis conditions. We saw high blood pressure and insulin user and cholesterol are all diagnostic conditions which could apply. We have age. The response can be age dependent. The gender can be age dependent. The person's of default diet can impact the conclusion. And the population may be a different mammal than humans. Yes, different mammal. We find that actually a majority of studies which we find useful are not on humans because trying to get studies done on humans is hard, especially well-controlled controlled studies involving diet. With an animal, you can precisely describe a diet that the animal is on and absolutely certain it keeps it. You ask a human to do something low glycemic diet and you find that many people will claim it but aren't doing it. Other people are doing it with some interesting twists, which means your study becomes fuzzy or unprecise. So often mammal and vet studies are wonderful for dealing with bacterial shifts. It's nice when it's in human because sometimes mammal studies do not transfer over to humans, unfortunately. That is the issue we'll deal with more a little bit later. And last thing is the microbiome processing pipeline. Each pipeline will come up with different microbacteria just being reported, and they may be same sample, same physical data file sample you get from a sequencer processed through different pipeline may say something else has changed than what your first pipeline did, which adds another degree of indirection, and I have other presentations dealing with that fact. But basically, rules are not bidirectional, and rules often are actually significantly complex, literally to get properly encoded. I mean, you got a ton of information which are preconditions for what the action or the response seeing. Couple thing is, outcomes are never certain. Studies may cite or report or not report non-responder. For example, I have two 2025 titles here. One deals with risk factor for non-responses, and where it's, hey, they found certain things which, if the person has this, they are non-responder. Oh, wait a minute. These suddenly becomes part of the conditions, the if blank, 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 blank part of the fact statement. And so we have to consider that the outcomes should always have a probability, somewhere between 0, no chance, or 1, which is very, very likely, or in fact, guaranteed. But guaranteed is always suspect, because there will be a percentage which will not respond, which will not behave the normal way. So it's always suspect, so you end up having to have a number somewhere between 0 and 1. Getting those numbers is another art in itself. When rules have only some of the conditions being matched, the question is, what do you do? Do you use the rule or not? One solution is easy. Okay, no, I don't want to take any risk. I'll discard it entirely. If we don't have a precise match, we ignore it. Okay. The reality is that you may run out of rules. You may have not a single rule left that can apply. In other words, it becomes inconclusive, no opinion, or you may have a very, very small number of rules, meaning that one particular study, which may not really apply that well, is all you have to work from. Generally, when we have a difference of conditions, we usually want to downward scale the odds. In other words, instead of, let's say, the odds were 0.9%, because of we're dealing with mice, and we are dealing with somebody which was on a Western diet, not a high-fat diet. There's a slight difference. Then instead of 0.9, we may want to scale down to 0.6 for the chance of this modification being successful. Those numbers are a statistical challenge or issue, and I will not deal with that explicitly apart from mentioning it. So the purpose of the expert system is to generate suggestions. And what we want to do is identify the items that have the highest probability of having a desired effect. From my experience, I often see this is a suggestion which are expected to have some positive effect, being 400 or 500 items, mainly because I have a lot of items in a database. And really, you don't want to toss your client, your customer, your patient 500 items to do. They could be overwhelmed. So what we want to do is identify the ones with the highest probability of having a desired effect. And often multiple suggestions may be generated from it. So what we want to do is we want to make suggestions based on those over some threshold. Okay, now let's look on to the practicality of a full expert system versus a reduced expert system. And it's sort of the difference between doing a sketch or doing a detailed watercolor or detailed oil painting, or getting out a Hasselblad to do a high resolution picture. All ways of capturing an image all have pluses and minuses to that. So a full system generally requires a large amount of precise rule writing. You have to put in all the conditions, making sure it's absolutely complete, and the actions you have to be absolutely complete in it, and including what the things like what is the probability, how significant the probability is, generate estimators when at all practical, and what percentage of responders are not responders. So you got a lot of information to encode. Now, that's where you can go and get all the information in, but now you come to having the fun of the time to execute all the rules. And that can become excessive because you may have to literally iterate through the rules 40, 50, 60 times because of lack of matching of conditions. So you end up having to, okay, we don't have enough here, we need to go back and we need to adjust some of the rules so that we exclude a condition and see what comes out. So it becomes an iterative process, and it can be recursive and very excessive for time. Also, often we need a complex inference component may be needed. Bacterial inferences are covered in different talk, and basically it's a question of if something, a study says, okay, it modifies lactobacillus, do we take that information and apply it to Pneumobacillus reuteri, which traditionally has been under Lactobacillus reuteri but is now moved elsewhere? Is that the same or is it not the same? What type of inferences do you make? Does one affect the other, and how positive are the same, or do we keep them absolutely isolated from each other? That's our partially philosophical but also practical thing. Now, on the flip side, we have a reduced expert system, which basically one that arbitrarily ignores many of the conditions. It's just basically say, we're not going to bother tracking that. We're not going to bother tracking that. We're not going to bother tracking that. In other words, we know we are going to be imprecise, perhaps potentially incorrect. But what we end up with is the hope of the result is going to be good enough. Not perfect, but good enough. And to give a practicality, the microbiome prescription does a reduced expert system, and basically it has 99,402 individual created facts. That would be 99,402 very long, very detailed statements with a full system. From that one, with limited inference, I mean limited inference, we end up with 7 million facts are used by the expert system. 7 million facts that has to be evaluated. And that came out of almost 19,000 individual studies. And we have, in terms of bacteria, to a selected, not all, to selection condition, we have something like 13,000 rules there. So we end up having a good chunk of data, and we actually get good performance using it, as in people will upload it, click, and within a minute, we will get suggestions computed out, and the suggestion will be computed out with the audit trail available too. So it's one compromise. You could go and do the full expert system, which is absolutely fine. I would encourage you. I really would love people to produce some of them with equal depth, because I want to see whether or not the reduced expert system, good enough, is well within the range of the full system. I went to reduced system because basically the data entry and everything else has been a solo operation, a smart solo operation, but I think a solo operation. And therefore it was done on the practicality of how much time is available to do it. It was resource constrained. So it was based on that. Resource constrained ended up with a reduced system. And that is always a question you have to do. How much resources do you have available? And is it worth putting in those extra resources? Let's take a quick look at common language for expert system. Lisp, Prolog, Clips, Scala, Ada are probably the most popular ones. We can also have a bunch of common languages if you're using various libraries which are available for them. There's Python, which is very popular, C++, C#. Each one has a difference in terms of performance. For example, Python is an interpretive language, so it tends to be slower than C++. C# tends to be a little bit slower than C++ and often faster than Python. So once you figure out the language you want to start encoding in and making sure you have a system that will be able to evaluate all your rules. In other words, set up a small prototype, put in your rules, and see if it logically comes to the appropriate conclusions. And do that early before you invest or say going with a particular language. Make sure it does it, and perhaps even if you are pragmatic like me, go and implement it in half the languages or 3/4 of the languages suggested and see what the performance difference is with the same input set. That may cause you to be biased toward one. It will show you how much work it is to code in each one and also indicate the performance characteristic. Performance and resource required is a critical factor for this type of expert system. Having over 3 million facts or 3 million equations to evaluate it should be expected. The question is the system supposed to be interactive, as in the data goes in and the user gets a response in a reasonable time? A reasonable time, I would say up to 2 to 5 minutes. Or is it something suitable for batch processing? It goes off and a PC somewhere in the boonies goes and grinds away for 5 hours to process one simple sample. Logic tracing should be part of the design. The result should also indicate, okay, the reason this suggestion is being made is because of these studies, 1, 2, 3, 4, 5, 6, and should allow it there so that user, for example, could be MD or could be consultant, has the ability to agree or disagree with the logic being produced. Why do you want them to be able to see it? Because if they disagree, they want to be able to express you why and point out where the logic problem is. You may have given too much weight to studies dealing with zebrafish, which for some reason blows out the results. So you want to have that information as feedback so you can iterate the study. And basically allows iteration and improvement of the expert system. Again, it's work. It's fun. It's exciting. I actually like the process. Now, once you think you have your system running moderately well, you want to do cross-validation. And that is test to see if the expert system is correct. You could do it by presenting a microbiome sample to a well-known expert and see what their suggestions are and comparing it. What I find is my preferred approach is go and find from studies what bacteria are seen for A conditions, generate your suggestions, and then for each suggestion, see if it's been tested for that condition and whether or not it helped. For myself, getting 85, 90, even 95% agreement between suggestions and things that help suggests that cross-validation for my trimmed down, reduced system is there, and getting anything over 70% agreement on an expert system of any type is generally considered to be very good results. Getting over 90% is almost dumbfounding. So, cross-validation. Check to make sure things are done. And again, the earlier you do it, the better it is, because you may have to say, wait a minute, this isn't working. Let's go back and try again, doing a different way, different rules, different modification. Hopefully your rules, your expert data is already saved in a machine readable format, so it's an easy matter to simply transform it to a different format to be able to use a different engine. Okay, let's look at the final tips and takeaway. First thing I cite is the closeness of rule fit, which is the fact that you may have a rule with 25 conditions to it. And the question is how close you have to be able to use that rule. How many of those conditions must apply? That is always a bit of a subjective question. With the reduced expert system, it is diminished. With the full expert system, it becomes far more critical, and especially how do you reduce it? Which ones do you allow to go out of the conditions first, and which ones do you keep to the very last? For example, age and gender probably is something you can dismiss earlier, where the person has diabetes is probably something there. And then you end up with some interesting theme where you have high cholesterol, age, and gender. Well, high cholesterol and age and gender tend to have association with them, which may mean you may want to take them all out as a combination or evaluate them as a combination. So the closeness of rule fit is a key factor. When you do that, depending on how close the rule is, you may end up with data sparseness. That is, there are not enough studies to be able to do something with, or to come up with more than one suggestion or two suggestions. So data sparseness is a habitual problem, although our numbers are, wow, you have 100,000 bits of information to work from. That should be more than enough. Well, not when you consider that we have 8,000 bacteria involved. So 8,000 into 100,000, that means we have 125 possible facts per thing. But the facts aren't evenly distributed. You find a horrendous number of facts dealing with H. pylori or with bacillus, with any one of the nasty infections, just a bountifulness of them. And then the rare bacteria, you may find practically nothing on. It may be lucky to find a single study. Next question is the inference. Often the studies report only at a genus level or a family level. And do you take that information and do you make inferences from a family to a genus, from a genus to a species, etc.? And do you go up or do you go down or do you go both ways? Remember, the results are going to be not deterministic. These are probable results. So you need to make sure you keep probability and odds throughout your expert system. You cannot just go and become definitive and deterministic. Don't be arrogant. Go probability. And last thing is knowledge is constantly changing. Your mechanism needs to always be able to, ideally on a regular basis, for myself, basically once a week, I run a extract from PubMed and walk through literally typical week, and I walk through 600 studies, many of which I can pre-exclude by using smart text parsing, as in know if it's dealing with a sledge from a agricultural system. The study is automatically excluded. Other cases, it will be included. So the mechanism to be able to constantly update your database is essential, especially when new data becomes available or when new treatments become available. So let's look at some final text, some key takeaways. The expert system you produce is a proprietary. It belongs to whoever funded it or created it. So it's proprietary, simple as that. I have my own system. It's proprietary. It's a trade secret. I don't give it out to somebody so they can see how it works. It produces results. The results are good. Okay, you can use it. I license it, but I'm not going to give away exactly how I'm doing things. I've described how you should go about creating your own expert system, which then becomes your intellectual property, etc. My own preference is do not seek a patent on it. Keep it as a trade secret, because the moment you make it a patent, you're giving away the farm for what you're doing it. The data that you use is likely not proprietary. You can't claim exclusivity unless it comes from your own internal studies, which is possible. I have such in my system, but I'm actually freer because I make all the source data available and I'm sure what the results is, and I can make use of that, and that's sweet. Okay. We have, with any published studies, generally using for expert system would be deemed to be fair use in terms of copyright. So there's not a problem there. If you can get the full text of the study, you should be happy and singing and good. It would be fair use. Again, not a legal opinion. This is just my general belief. If you have concerns, get a formal legal opinion on it. The expert system should have an audit trail or backtracing we should be back to the article which you are using as a basis. You should not go and explain how you process the article or anything else. Keep that proprietary part of the trade secret. To point out the article, yeah, so somebody else could read it. They could come to different conclusions from the article, which is fine, and they could challenge you, which is fine, and it's preferred. That's how we learn. But you should not be disclosing exactly how you are processing data in the article. That should be kept proprietary. When we look at resources, for example, human resources of encoding the data, as I said, I have 100,000 manually reviewed facts. That is a fair amount of time. Is the cost versus the benefits versus the delivery time? How long is it going to do for your crew to enter in 100,000 facts? Um, and how long is that going to take to do it? And what is the cost of their man hours and man time? Even if you're hiring PhD students at absolutely unbelievable cheap rates, which you should be ashamed of yourself, that's far less than what they actually are worth. Then you want to evaluate the cost to produce a system. Of course, there's the expected value of it at the end, but you want to judge that carefully, because if you overinvest, you may find yourself not having a deliverable project, and you may not necessarily have the ability to sell your existing fact database to somebody else. You may or may not. That is always a question. And continuous update, doing monthly addendums. Myself, I go for weekly addendums just for it. Okay, so that basically covers my lovely monologue on using expert systems of the microbiome. My contact information is there, and feel free to contact me if you have questions or concerns. But with that, I'll shut up for the moment. Okay, have a good day.